Hi everyone, I'm Josh Chima, and this is our group's presentation on the vehicle routing problem and approach using reinforcement learning. James and Aziz are the other members of our team who you'll hear from soon. So the vehicle routing problem. The essential question in this problem is, what is the path a set of vehicles should take in order to deliver goods to customers within a given time frame? Traditionally, this involves multiple vehicles, a depot where the storage and the goods are kept, and customers that have distinct demands. They have different amounts of goods they need and different time windows in which they need them. It's a really challenging problem. It's considered to be NP hard, where NP means non-deterministic polynomial time. It's a complexity class that tries to capture how challenging a problem is. And to say that something is NP hard means that it is at least as hard as any other problem within this class. So I'll talk about the data set that we used for the first approach we took, which is to build a deep queue network. It's actually 57 different data sets that are synthetically derived and publicly available. They each have 100 customers with X and Y coordinates, and they have a certain demand, a time that each customer is ready to get a delivery, a time that a delivery is due by, and a service time, which is how long it takes for the truck to be unloaded there. And each data set is built so that it poses unique challenges within it that's different from all the other data sets.
Hi, I'm James, and I'm here to talk you through our deep queue learning approach. So this is how we formalize the framework with all the customer attributes stored row by row in a data frame, and similarly for the vehicles, so we have access to both the locations and the loads of each one. Flattening and concatenating these structures forms our state, and to help reduce the state size a bit, which speeds up the process, we redefined all the X and Y coordinates jointly as distance to the current vehicle, and we also redefined times as relative to the current game time. We used a lot of normalization to scale the data, which should help the training process. Having multiple vehicles poses a challenge, and we navigate this by keeping track of which vehicles are idle and which are busy. At each step, we select any idle vehicle at random as the action vehicle, and if none are available, we just fast forward the game's timer until the next vehicle becomes free. This approach avoids having to laboriously iterate the gameplay until this happens, which is a really important consideration given that each iteration is actually quite costly. There are many ways we can define the rewards, and we tried a lot during the course of this project. The most successful approach was to reward vehicles when they deliver cargo, to penalise them for distance travelled, and to end the episode immediately if anyone's delivery is late, with a large negative reward. This was probably the most successful approach because it's fast, and you'll notice that speed has become a central theme of our implementation. Of course, this early termination also results in fewer iterations and thus less learning within each episode, but it does produce the best results. After all of this, we reduced the computational workload by only considering 10 of the 100 customers from each problem. We found good solutions, which you can see in the graphic. After around 1,100 episodes, the AI learns to make consistent positive rewards. And whilst the resulting routes weren't quite optimal, because you can see they visited the same customers twice on occasion, we can see that the algorithm is learning well, and a little bit of extra time would help optimize the route even further.
Hi, this is Aziza. So in addition to DeepQ Network, we've also experimented with attention model, which has been introduced in the paper by Peng et al. So it's very similar to neural machine translation, which encoder extracts syntactic structure and semantic information from source language text. Then the decoder constructs target language text from the features given by the decoder. So VRP uses attention model by first creating structural features of the input instance, which are extracted using encoder, and then the input is constructed using decoder by predicting the distribution over nodes, and then one node is selected and appended to the end of the partial solution. So in addition to attention model, this paper also introduced us with dynamic one, so I'll be introducing in the upcoming slides. So the way how the attention model works is based on the graph attention network, which is used to encode node features and embedding in the context of a graph. So it creates very complex graphical structure. So for each three-dimensional input node. About 128 initial nodes embeddings are computed using linear transformation with learnable parameters. So the initial node embeddings are fed into first layer of graph attention network and updated about 3 times. So each layer consists of 2 sublayers and having multi-head attention and the fully connected feed-forward neural network. So here on the right figure, you can see that the message stream and encoder, which actually aggregates the message from each node and then updates here the dpod embeddings and here the customer embeddings. So considering that in the vanilla architecture, feature embeddings are only updated only once in the beginning. This paper introduced the dynamic attention model, where the embeddings of each node will be immediately recomputed when the vehicle returns to the dpod. So here in the B, you can see that how it's actually updated in each construction time step. So here you can see our results. We've actually experimented with epoch of 4 and epoch of 20, and as long as the epoch is actually improving, so does the performance of the model as well. So thank you, and Josh will be concluding the presentation.
And so that wraps up our presentation. Thank you for your time and attention. In summary, we tried to challenge the vehicle routing problem, which is quite a challenging task. We learned a lot in the process, and we hope you did too.